In this video, we will talk about functions and its types. We'll introduce what function is, what are the different types of functions. We'll talk about various properties of function, composition of functions, and at the end, we will talk about inverse of the function. Function f is actually a subset of binary relation which associates each element of first set, that is capital X, to exactly one element of second set, that is capital Y. And function is denoted as f colon x to y. So this is said that function name is f. The first set from where we are reading the element is x, and the element of x are mapped to elements of y. So y is the another set. A relation R, which is subset of Cartesian product of sets x and y, is a function if it holds the following property. For every element small x belongs to set capital X, there is exactly one ordered pair in R with the first component x. That is the first condition. However, it is not compulsory that all elements of y are connected to x. So when we can say something is function or relation is a function, when every element of first set x is having association with some of the elements with y. And there should be exactly one such ordered pair. It means one element of set x cannot be connected with two different elements of set y. Right? And another thing is that it is not necessary that all the elements of y are connected. Elements of x must be connected, but for y there is no such restriction. If relation holds these two properties, then it is a function. So ultimately, all functions are relations, but not all relations are function. So we can say that relation is subset of Cartesian product and functions are subset of relations. If we look at this, x is ABC, y is 1, 2. So A is connected with 1, B is connected with 2. So all the elements of y are connected, but element C, which is in x, is not connected in any element of y. So this is not a function. The condition is that all the elements of x must be connected with some of the elements of y. Here, all the elements of x are connected with some of the elements with y, but still it is not a function because B is connected with two different elements. So there are two pairs, B, 2 and B, 3. There should be only one pair for every element of x. This is a function. E is connected with 1, B is connected with 3, C is connected with 4. So all the elements of x are connected with some of the elements of y, and they have exactly one ordered pair for every element x. Okay? So even though element of y is not connected, that is okay. That is fine. Still it is a function. Let us talk more on this function. So pair x comma y, which is in f, we can also write it as a f of x is equal to y. So y is a dependent variable, x is independent variable. When we put the value of x into function f, it will produce y. So typically we write function as f of x is equal to y. So x is the input and y is the output of the function. Set of all the first elements of members of function f will form the domain of the function, and it is denoted by dom of f. So whatever values element x is taking, that is called domain of f, and set of all the second elements of members of f form the range of f, and it is denoted by range of f. Let us discuss various types of function. The first one is one-to-one function. So function f from x to y is said to be one-to-one if no two elements of x have same image in y. That is f of x1 is equal to f of x2 if only if x1 and x2 are same. If all the elements have a different image in y, then it is called one-to-one function. For example, f of x is equal to x plus 2. So for any value of x, there will be unique y. So if my x is 1, 2, 3, then y would be 3, 4, 5. We just are adding plus 2 in an element of x. So 1 is associated with 3, 2 is associated with 4, and 3 is associated with 5. So this function is one-to-one function. And one-to-one functions are also popularly known as injective function. If we talk about this function, it is not a function at all because x4 is not connected. This is also not a function because x4 is connected with two elements. This is a function, but it is not one-to-one because two elements x1 and x4 have same image in y. It is not possible, it is not allowed. So this is not one-to-one. Though it is a function, it is not one-to-one function. And this one is one-to-one. All elements of set x are connected and every element of x has a unique image in y, or they have a unique projection in y. So this is one-to-one function. The second type is an onto function. The function f from x to y is said to be onto if every element of y is image of one or more element in x. That means now the condition is that all the elements of set y must be connected with some element in x. And such functions are popularly known as surjective function as well. Consider the function f of x is equal to x mod 3. And if we take x is equal to 1 to 7, then the mod 3 would be either 0 or 1 or 2. Right? 1 mod 3 is 1, 2 mod 3 is 2, 3 mod 3 is 0, 4 mod 3 is 1, 5 mod 3 is 2, 6 mod 3 is 0, 7 mod 3 is again 1. So all the elements shown in red in x, their mode is 1. All the green elements shown in x, their mode is 2, and all the blue elements have mode 0. So if we plot it, then 1, 4 and 7 is associated with 1 in y, 2 and 5 in x will be associated with 2 in y, and 3 and 6 in x would be associated with 0 in y. So every element of y is associated with some element in x. Now that associativity could be multiple, no problem, but all the elements of y must be connected. This is function, but it is not onto function because y2 is not mapped with any element of x. It is not connected. This is onto function because all three elements y1, y2 and y3 are connected with some of the elements in x. Now y3 is connected with multiple elements. That is allowed. That is okay. For onto function, there is no such condition that it should be connected with only one. The only condition is that all y should be connected with some x. Third type of function is one-to-one onto function. So function f is said to be one-to-one onto function if it is one-to-one and it is also onto function. And such functions are popularly known as bijective function. So fx is equal to 3x minus 5 over r is one-to-one as well as bijective. If we look at this, this is one-to-one because every x has a unique image in y. This is onto because every y is having some association with x. So if we can find this kind of relation between x and y, then such functions are onto, one-to-one onto, or the bijective function. Let's talk about various properties of the function. In fact, there are three functions, floor x. So floor x is defined by this notation, and floor defines the lower possible integer. So if we compute the floor of 3.4, then lower integer would be 3. For 3.8 also it would be 3. So floor will always compute the smallest integer for given number. Smallest possible integer. So 3.4, its nearest small integer would be 3. For 3.8 also, the smallest nearest possible integer would be 3. Scaling of x will compute the next higher integer. So 3.4, and it is denoted by this notation. Scale of 3.4, that would be next higher integer, that is 4. And scale of 3.8 would also be 4. So floor and scaling functions are giving same value, whether it's a 3.1 or 3.9. And there is a third function which is round. So round function will return the closest or the nearest integer value. So round of 3.4. So on one side it is 3, on another side it is 4, but 3 is closer to 3.4. So that would result 3, and round of 3.8. So one side integer 3 is there, on another side it is 4. But 4 is more closer to 3.8. So round of 3.8 would be 4. In general, we can say that x minus 1 would be less than floor of x, which would be less than or equal to x, which would be less than or equal to scale of x, and that would be less than x plus 1. So this relation will hold for any fractional value. If I take x is equal to 3.4, then round of x, then floor of x would be 3 because it will consider the lowest closest integer, and the ceiling of that would be 4, because that will consider the next higher integer. And if we put this value x minus 1 less than floor of x less than or equal to x less than or equal to ceiling of x less than or equal to x plus 1, if we put all these values, then it will definitely hold this equation, because x minus 1 would be 2.4, which is less than floor of x, that is 3, which is less than or equal to x, that is 3.4. Again, it is less than or equal to ceiling of x, which is 4, and that is less than x plus 1, that is 4.4. For any integer x, if we do summation of floor of x by 2 and ceiling of x by 2, then that will always result into x. Consider x is equal to 7, then floor of x by 2, that is floor of 3.5, which is 3, and ceiling of x by 2 would be ceiling of 3.5, which is 4, and addition of that will lead to 7, which is x. So that is proved. So these are the some of the important properties of the ceiling, floor, and round functions. Composition of function are typically used to simplify the series of functions. So suppose I have to apply some function f, then I have to take the apply function g on that, then I have to apply function h on that. So that process might take a long time if we apply the functions individually on those elements. Rather than we can find the composite function, so that we only have to apply single function on the data rather than applying series of functions. So composition is defined by the circle between two function name. So f composition f is nothing but it's a function of f of x, and f composition g is given as function of g of x. So first we will apply function g on x, and then we have to apply function f on x, f on that data. We have function f of x is equal to x square and g of x is equal to x cube. So if I have some data, say for example 2, and I have to apply first f and then g. So if I don't do the composition, then first I will take the square of the 2. I will compute square of 2, so that will be 4. And then I will apply function g on that. That means I have to cube that. So cube of 4 would be 64. So I had applied two function on the data. Let us see how we can compute the composition. So f composition f would be f of x. Now we know that our f of x is x square. So now we just have f of x square. So whatever element we are passing, again we will take the x square of that, because f of x is defined as a x square. So ultimate would be x power 4. So we just have to apply this x power 4 on data instead of applying function f twice. Similarly, f composition g is defined as f of g of x. So g of x is x cube. So we have f of x cube. And function f, the definition of function f says that we have to square whatever input we have. So square of x cube would be x6. So instead of applying function f g first, then applying function f on that, we can directly do x power 6. So there is no need to apply two functions, only one function or one computation is enough. G composition f is given by g of f of x. F of x is x square. So we are left with g of x square. And function g does simply cube of input. So cube of x square would be x power 6 and g of g would be x power 9 in a same way. Let us consider somewhat more complex example which will make sense. Suppose I want to apply function f on x and then I want to apply the g. So first I need to take square of x, then I will add plus 9 into that. Whatever answer I got, that I will feed it into g. So g will multiply that input by 4 and then it will add 5 into that. So that's a lengthy process. Let us simplify that process by taking the composition. So if I take f composition g, then that will be equivalent to f of g of x. So g of x is 4x plus 5. So that we are passing into f. Now we know that whenever we pass x into f, it will square it and will add plus 9 into that. So the simplification of that would be 4x plus 5 whole square, that is a x square plus 9. And when we simplify, that would be 16x square plus 40x plus 25 plus 9. And the further simplification would be 16x square plus 40x plus 4. So instead of first applying 4x plus 5 on input and then doing x square plus 9 on that, we can directly write 16x square plus 40x plus 4. A single operation and we are done. In same way, g composition f we can compute as g of f of x, that is g of x square plus 9. From definition, we already know that when we provide some input x to function g, it will multiply that value by 4 and then add 5 to that. That is 4x plus 5. So simply 4 times x square plus 9 plus 5. Simplify it, so will be 4x square plus 36 plus 5. That is ultimately 4x square plus 41. Clear? So you can see the advantage of doing function composition. We just have to do 4x square plus 41 and both the functions will be applied. First f and then g. So FOG is not same as GOF. Remember that both are different. You see, in first case we have 16x square plus 40x plus 4. In second case it's 4x square plus 41. Let us see how to compute inverse of a function. If f is a function over a to b and it is a one-to-one function with domain a and range b, then its inverse function f of f inverse has domain b and range a. So domain and range will interchange when we compute the inverse of the function. So domain will become range and range will become domain. A function only has an inverse if it is a bijective function. Otherwise, we cannot compute the inverse of the function. The inverse of a binary relation R, which is defined over Cartesian product A and B, then its inverse is denoted as R inverse is equal to pair B comma A such that AB is in R. So if AB is in R, then BA should be in the inverse of that relation. Function f of x is equal to y. If it is given, then its inverse we can write f inverse of y is equal to x for any y in B. So for every x belongs to A, f inverse of f of x is equal to x, and for every y belongs to capital B, f of inverse y is B. So originally function is defined for f of x is equal to y. Its inverse will be equivalently f inverse of y is equal to x. So when we take inverse of f of x, then that will give us the same x, that is x. And when we take function of inverse of y, then that will give us the y. So these are the two important property of the inverse function. Let us see how we can compute the inverse. So that's a three-step process. In first step, we have to replace f of x by y. So initially we have f of x is equal to x cube. So that will be y is equal to x cube. F of x we have replaced by y. In step 2, we have to solve it for the value of x. So y is equal to x cube will become x is equal to cube root of y. And finally, we have to replace x by inverse f inverse of x and y by x into the output in step 2. So x is equal to cube root of y will become f inverse of x is equal to cube root of x. So that is the inverse function of given function. Consider another example, that f of x is equal to x plus 1 divided by x. So step 1 says that replace f of x by y. So we have y is equal to x plus 1 by x. Step 2 says that solve this equation for the x. So we are multiplying x on left hand side. So that will be xy is equal to x plus 1. Take x onto the left hand side. So xy minus x is equal to 1. Take x common. So we are left with x into y minus 1 is equal to 1. And solve it for the x. So x is equal to 1 upon y minus 1. In step 3, we have to replace x by f inverse of x and y we have to replace by x. And that will give us the inverse of x. So that is f inverse of x would be 1 upon x minus 1. So when we do this, the domain of f will become range of f inverse and range of f of x will become domain of inverse of that. Let us test your learning. State properties of functions. What do you mean by one-to-one function? And give 2 examples of such functions. What do you mean by onto function? Give examples of such 2 functions. And what do you mean by bijective function? Give examples of 2 examples of such function. And find f composition g and g composition f for the function f of x is equal to x cube minus 4 and g of x is equal to 10x minus 4. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.